Welcome to the Explainer. So glad you're here. Look, if you're a focused learner, ready to finally crack the code of Cambridge IGCSE Additional Mathematics 0606, you are in exactly the right place. Our mission today, we're going to completely demystify these algebraic concepts and, bridge that annoying gap between abstract math theory and actual solid exam strategy. Let's get right into it.
Okay, here's our game plan. We'll kick things off with math in the real world, then jump straight into mastering modulus. After that, we'll weigh graphical versus algebraic methods, dive into quadratic substitutions, decode cubic inequalities, and wrap it all up by tackling the exam.
All right, Section 1, Math in the Real World.
So you might actually recognize this thing. It's a 1 meter square quadrat. Biologists literally toss these on the ground to sample plants and bugs in a specific area. But look a little closer at the grid itself. To actually describe the region it covers accurately, biologists rely 100% on the mathematical concept of an origin point, right in the center, with sides perfectly parallel to an x and y axis. It's basically biology perfectly mapped out by coordinate geometry. Kinda cool, right? Now, let's look at something a bit faster. Ever wondered how economical a 2017 Monaco Formula One car actually is? I mean, the 2017 Monaco Grand Prix was won by Sebastian Vettel in a Ferrari. But here's the thing. Vettel couldn't just, put the pedal to the metal the whole time. His fuel management was strictly governed by real-world mathematical inequalities. Here's the math on that. The race rule stated that total fuel used over the 260-kilometer race was capped at 105 kilograms. That's roughly 140 liters. So if we say fuel economy is E, the restriction is basically that E has to be less than or equal to 140 divided by 260. And that simple equation brilliantly gives us our answer, 0.538. At the absolute worst, Vettel's winning Ferrari got a fuel economy of 0.538 liters per kilometer. It's an extreme multi-million-dollar machine, but it's completely constrained by a simple algebraic inequality. Moving right along to Section 2, Mastering Modulus Functions. Okay, so what actually is a modulus? Denoted by those two straight vertical lines, it's really just the absolute positive size of a number. Think of it as the literal distance of a point from the origin on the x-axis. So the absolute value of 5 is 5, but the absolute value of -5? That's also 5. Algebraically speaking, the modulus of x equals x if x is greater than or equal to 0, and it equals -x if x is less than 0. Visually, though, this creates a pretty profound transformation. If you take your standard straight line graph and apply a modulus to it, any part of that graph that dips below the x-axis just gets reflected upward. The positive part, that stays exactly the same, but the negative part flips right up, which gives you this very distinct, sharp V shape. Honestly, remembering this visual rule is an absolute game changer for quick exam sketches. All right, on to Section 3, Graphical versus Algebraic Solutions. Let's see how they stack up. So your textbook is going to outline two primary methods here. First up, the graphical method. This requires you to actually sketch the V-shaped graph and the intersecting line, like if you were solving the modulus of 3x minus 1 equals x plus 5, and visually spot where they intersect. But wait, here's the catch. What if the graphs intersect at a weird fraction, like 1/3? Your hand-drawn sketch isn't going to show that clearly. That's exactly why we contrast it with the algebraic method, where we actually solve for both the positive and negative cases of the modulus. Basically, the graph gives you that great visual intuition, but the algebra, that's what prevents those little inaccuracies from costing you marks. Hey, real quick before we break down this next table, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Okay, back to the explainer. When you're dealing with modulus inequalities, structure is literally everything. This table is perfect for breaking down how to translate a visual number line into an algebraic form. If your modulus inequality is less than or equal to b, your algebraic form sits right there between a minus b and a plus b. On a number line, you draw this with solid circles, right? That shows those n values are included. But if it's strictly less than, you've got to use open circles because those endpoints are excluded. Honestly, if you master this table, you are never going to drop those easy marks on notation. Let's jump to Section 4, Clever Quadratic Substitutions. Take a look at this equation. X minus 3 times the square root of x equals -2. Looks pretty intimidating, right? But we have a super simple 3-step strategy for this. Step 1. Substitute x with u squared. By doing that, suddenly the square root of x just becomes a simple u, and like magic, the equation transforms into u squared minus 3u plus 2 equals 0. Much better. Step 2. You just solve this standard quadratic to get your u values, which you then square to find your x values. But hold on, do not stop there. Step 3 is absolutely crucial. You have to check all your calculated x values by plugging them back into the original equation. And that brings us to this massive warning right here. Why do we have to check them? Well, let's take the equation x minus the square root of x equals 6. If you run the substitution method, the algebra tells you that x could be 9 or 4. But watch closely what happens when we plug 4 back in. 4 minus the square root of 4 is 4 minus 2, which equals 2. And last time I checked, 2 definitely does not equal 6. The mathematically correct algebraic answer totally fails in the reality of the original equation. So you have to actively reject x equals 4. Otherwise, you are definitely going to lose marks. Moving into section 5 now, decoding cubic inequalities. Okay, so when you're asked to sketch a cubic, the very first thing you need to look at is the coefficient of the x cubed term. Seriously, it dictates the entire flow of the curve. If you have a positive x cubed term, it means the curve generally travels upwards. It'll start down in the bottom left and end up in the top right. But a negative x cubed term, that flips its destiny completely. The curve is going to start top left and flow downwards to the bottom right. Let's put that into practice. Say you're asked to sketch y equals the modulus of 3 times x plus 2 times x minus 1 times x minus 7. First rule, don't panic. Just find the x-axis roots first by looking at your brackets. The curve crosses at x equals -2, 1, and 7. Easy. Now sketch the normal positive cubic curve right through those points. Once that's done, just apply the modulus rule we talked about earlier. You literally just take those bottom loops that are dipping below the x-axis and reflect them straight upward into positive territory. Just like that, a crazy complex equation turns into a really simple, structured sketch. Finally, section 6, tackling the exam. Let's bring it all together. All right, before we dive into a real past paper, here is your ultimate summary checklist pulled straight from the source material. Number 1, always solve modulus equations via squaring or dual case algebra. That's how you avoid those pesky graph reading errors. Number 2, when you're dealing with 2D inequalities, identify your feasible regions by cleanly shading out the areas you don't want. Number 3, always beware of false roots in your u-squared substitutions. Test them. And number 4, let that x cubes term be your guide for the overarching shape of your cubic sketches. Okay, let's look at a real Cambridge past paper question. This is from paper 23. It asks, how many values of x satisfy the modulus of 2x plus 3 times 2x minus 7 equals 2x? Now, notice the phrasing here. It's not asking what the values are, it's just asking how many there are. So, how would we actually deploy our methods for this? The best strategy here is honestly brilliant in its simplicity. First up, you sketch the modulus of the quadratic curve. So find your roots, draw your U-shape, and then flip that bottom part up so it makes a W shape. Second, you just draw the straight line y equals 2x right over the top of it. Because you're visualizing both on the exact same axes, you can literally just count the number of intersection points. You're using your graphical vision to find the how many. And if the question had asked for exact coordinates, well, then you just switch gears to your algebraic precision to confirm them. It's the dual path method at its absolute finest. As we start to wrap things up, I want to share a really cool quote from the textbook by the brilliant mathematician Pierre-Simon Laplace. He wrote, "It is India that gave us the ingenious method of expressing all numbers, a profound and important idea." You know, it is so easy to get bogged down in exam stress and all these formulas, but never forget that these algebraic symbols, these modulus lines, the inequalities, they are historic, profound tools of human ingenuity, and you are learning to master them. And that brings us to the end of this explainer. You are now fully equipped with the graphical vision to see the actual shape of a problem and the algebraic precision to lock in the exact correct answers. The structures are there. The rules are totally clear. So here's my question to you. How will you approach your next complex equation on that past paper? I highly encourage you to grab a practice exam right now and test these exact strategies. Also, remember to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Thank you so much for hanging out with me today, and keep on learning.